Hey everyone, thank you for stopping by. I am Abhishek Chattaraj, a master's student from IIT Madras, and today I'll be talking about the construction of hybrid waveforms using post-Newtonian theory and numerical relativity simulations for eccentric binary black hole mergers with the incorporation of higher order modes. This work was done in collaboration with Dr. Chandra Mishra and Dr. Anshu Gupta. So let me start with the motivation behind our work. A typical disadvantage of ground-based detectors is that they are not capable of detecting eccentricity from sources. This is because by the time the sources enter the sensitivity bands of these detectors, most of the eccentricity is lost. But with the advent of LISA, we will begin to successfully detect orbits with significantly moderate to large eccentricities, and being space-based detectors, the signal-to-noise ratio would be very high, which would help us in revealing higher order harmonics present in the gravitational wave signal. Now, for mergers involving high eccentricities and high mass ratio components, the higher order modes become very important, especially for parameter estimation studies and source modeling results. Hence, we should root for a way for building template waveforms with prescription of both eccentricity and higher order modes in them. And as a first step, we construct the hybrids for the complete evolution of these binary black hole mergers through the inspiral-merger and ring-down stages. To compute an accurate waveform, we need to describe the various stages that characterize the evolution of the binary merger. Post-Newtonian theory provides us with accurate expressions for the early inspiral stage and numerical relativity methods for the late inspiral-merger ring-down, and in between we have sort of a gray area where it is not justifiable to depend on inputs from either PN because it cannot be trusted too close to the merger because the approximation breaks down, or numerical relativity due to length requirements which makes long simulations difficult. Thus we need to combine them in an appropriate manner and build some sort of a hybrid of the analytical and numerical data in order to obtain a correct representation. And this is where the process of hybridization comes in. So for inputs, we begin with the PN expression for the evolution of the gravitational wave amplitude, phase, and orbital eccentricity, etc. Here we see the full 3PN expression for the dominant 2-2 mode as computed in a 2019 publication by Boetzel et al. And for numerical relativity waveforms, we use the simulations provided by the SXS collaboration as given in a 2018 paper by Hinder et al., which contains 23 different simulations of different mass ratios and eccentricities. Here Q denotes the mass ratio of the component binaries, and EREF and LREF are eccentricities and mean anomaly at some reference frequency. Now, a binary black hole merger description requires a 15-dimensional parameter space, including both intrinsic and extrinsic parameters, like the individual masses of the binary black holes, the spin of the black holes, and the sky coordinates like the RA and DEC, spherical angles, the distance to the source, etc. All of which can be written in terms of a complex time series in the plus and cross polarizations. Here we can see we are conveniently decomposing this as a sum of spin-weighted spherical harmonics and the strain from the individual modes LM. From theory, we know that the leading contribution to the complex strain comes from the L equals M equals 2 mode. So now, coming back to the generation of the waveform, we pick a NR simulation from the catalog and we produce the corresponding PN waveform using the same binary parameters of the NR simulation, and we evolve the post-Newtonian expressions. The hybridizing procedure involves choosing a convenient time window and determining the time and phase shifts which minimizes the difference between the PN and NR in that time window. So we run a minimization routine which pops up two numbers, say T0 prime and phi 0 prime, which yields the best matched PN and NR waveforms. Then we produce the hybrids by multiplying with a weighting function tau of t, which basically does the work of stitching the two waveforms together. Here we show our hybrids for a representative case SXS BBH 1364. For all L equals to M modes till L is less than equals to 5, the NR simulation is shown in red and the PN waveform is shown with black dotted lines. Our IMR hybrid is represented as a piecewise function which perfectly resembles our Pn approximant at low frequencies and the NR at high frequencies. Hence, this entire waveform is a combination of analytical as well as numerical data, beginning with the Pn waveform, followed by a transition region which is a combination of both Pn and NR, and lastly by the NR waveform from the SXS catalog. Thereby we see that in a PN-NR hybrid, each region of the inspiral-merger ring down is constructed using data that is most accurate description of the event in that region. The width of the hybridizing window is something we wish to look further into. So to summarize our work, we have constructed hybrids for all L equals to M modes till L is less than equals to 5. For all 23 NR simulations provided in the catalog, which contains 3 circular binaries along with 20 cases of eccentric sources. A natural way to progress from now would be the modeling of the amplitude, phase, etc. in the frequency domain. And as per the availability of numerical simulations, we aim to do the same thing, that is, we aim to construct hybrids with moderate to large eccentricities, which will be directly useful for the data analysis in LISA. And with that, I end my talk and thank you for joining.